So in today's class, we are going to see the C program for binary search tree operations. So first, we are going to create the necessary structure for storing the binary search tree nodes. And first, in line number 1 and 2, the necessary header files are included. And in binary search tree, the node is going to have totally 3 fields. It is similar to normal binary tree only. 2 fields are for storing the address of the left child and then right child, and they are the pointer fields. And 1 field is for storing the data. So in case of the pointer fields, in line number 6 and 8, left and right are declared as pointers by means of star, and they are pointers to node of the binary search tree type. So the data type of those 2 pointers are declared as struct binary search tree. And once we finish the structure, we are going to use a type def to give a short name for this binary search tree so that we can easily refer that in our program. So I am declaring type def struct binary search tree, and this is a existing data type. Struct binary search tree is the existing data type. For that, we are going to give a new name, that is node. Then throughout the program, I'm going to use a certain pointer variable. So I'm declaring node star as a pointer variable. New is a pointer variable, and the data type is, since it is a pointer, I have a star, and it is a pointer to a node of this binary search tree. So since we have given the new name as node, I am writing node as a data type. Now let us see how to perform the insert operations. In case of insert operation, we are going to use the function insert. For this function, we need to pass 2 arguments. The first argument is the root of the tree where we are going to insert the data, and the second argument is the data to be inserted. And out of these 2 arguments, the root is a pointer field because we need to give the address of the root node. So it is a pointer, whereas the second one is the item to be inserted. That is nothing but whatever is the data type you have declared here for data, that should be given. So here it is integer. So first, let us see how to insert a node in the binary search tree. So first, if your root is null, root is a pointer which is storing the address of the root node. If that pointer is null, it means that there are no nodes in your binary search tree, it is initially empty. So first we are checking if root is equal to null. If so, you need to create a new node, and that node should be inserted as a root node now. So for creating the new node, I'm going to use the malloc function. To this function, we need to pass the size of the memory to be allocated, and it is always better to go for size of, instead of giving the number of bytes directly like 10, 20, because the size of the integer will depend upon your compiler. So we are giving size of node, and it will allocate the necessary memory, and finally it will return a starting address of that memory location, and we are going to store the starting address in a pointer variable called new. So this new is already declared as a pointer to node. Then after you have allocated the memory, the next step is you store this 11 in the data field, as well as in both the pointer fields we have to store null. So why we are storing null in both the pointer fields? The reason is, in a binary search tree, whatever node you are inserting, that will be always inserted as a leaf node. So in case of leaf node, it is not going to have any children. So we are going to store null in both the pointer fields. So in new arrow data, I am storing the item, which is nothing but the argument I am going to pass to the insert function. That is the data to be inserted. And then in the left and right pointers of this new, I'm going to store null. So new arrow left is equal to new arrow right is equal to null. Then once we do that, only this particular structure will be created. Still, the root is having null value only, but we have to store the address of the new node inside the root pointer. So the next step is we need to write root is equal to null. Once this is done, then only the root will have the address of the root node. Now, whatever node we have created, that is the root node. So that address is properly reflected in the root pointer now. Next, I'm going to insert the second number now. First, I have inserted 11. The tree is now existing. Then I'm going to insert a new data 5. So for this, I have to call the insert function second time. So this time also, I have to pass only the starting address of the root. That is, whatever is available in this root pointer, that should be passed. Every time we need to pass only the address of the root node. Then the second argument is item to be inserted. This time I want to insert 5. So in case of binary search tree, item is inserted into the tree based upon the value of the root node and the value of the data to be inserted. So first we have to compare this new data 5 with the value stored at the root node. 5 is less than the value at the root node, that is 11. Therefore, the new node 5 should be inserted as a left child of the root node. Otherwise, if it is greater, it will be inserted as a right child of the root node. So for this, we have to write the necessary steps. So we are writing now if item, that is data to be inserted, is less than root arrow data. So we are comparing this 5 with 11 now. If it is less than root arrow data, I need to insert the new data in the left subtree of the root node. So what is the meaning of that? I'll create first a new node, then whatever is the address of the new node, that should be stored instead of this null. Here now 11 is having the left subtree as null. That means there is no left subtree. But now we are going to insert a new node 5 in the left subtree. Therefore, after you insert, whatever is the starting address of that particular node, that should be stored instead of null. So you can look at this step now. If item is less than root arrow data, I am going to again call the function insert. This time I am going to pass two arguments. The first argument is not root because we are not going to insert the data in the root node. We are going to insert the data in root arrow left. That is, item will be inserted in the left of this particular node. So I am writing now root arrow left as a first argument, comma, item to be inserted is passed as the second argument. Once this function insert is called, it will create the memory for the new node as we have seen in the previous slide. After that, it will allocate both the right and the left child as null. Finally, it will return the address of the new node. That is, let us see the next slide so that you will understand. It will return the address of the new node. So now you can look at here. I have created the new node. In the new node, in the data field 5 is stored, and in the right and the left pointers, null fields are stored because now this new node will be inserted as a leaf node only. And now this 11 is not going to have null in the left pointer. Instead, it should have the address of this new node. So for that, what we are going to do is we are going to store the address, whatever is returned by this node, inside this null pointer. So for that only, here we are writing root arrow left is equal to insert root arrow left comma item. If you don't write this root arrow left, the node will not be inserted in the left child of as a left child of this particular node. Okay, so once you write that particular step, whatever is the address of this node, it will be reflected in the left pointer of this root node. So likewise, we can insert any node in the left direction. Now let us see how to insert a node as a right child. So for that, let us consider that now I want to insert 22 into the binary search tree. So again, I have to call the function from the main by passing the address of the root node. Then I need to pass the new data to be inserted, that is 22. First, I'll be comparing the data 22 with the data stored at the root node. So at the root node, I have 11. 22 is greater than 11. Therefore, 22 should be inserted as the right child of the root node. So for that, we are going to write the step. So else means when it will come to this particular part is the root is existing. Okay, and then it is not a left subtree, it is a right subtree. Then only we'll come to the else part. So now you are going to compare first. You are comparing whether item is greater than root arrow data. If so, you have to insert the item in the right subtree of the root node. So I am calling the function insert, and to this function insert, I should pass root arrow right as the address because I need to insert the new node at this place only. So this I can access by means of root arrow right, comma, pass the item to be inserted. Once the item is inserted into the tree, it will return the starting address of that new node. That address we are going to store in the right pointer of the current root node. So we are writing root arrow right is equal to insert root arrow right comma item. So now after that is executed, we will have the flow like this. First, the new node will be created, memory will be allocated. Then in the data field, we are storing 22. In both the pointer fields, we are storing null. After that, now here we have null only. That null should be changed. So it should be changed as the address of this particular node. Okay, so that only we are doing every time when we are inserting our element either in the right subtree or in the left subtree. Now, finally, as I already told you, every time when you do the operations, you have to return the address of the current root node to the function from where it has been called. Every time you are calling this from inside a function only. So you have to return the address of the current root node. The reason is your tree is now modified. Whenever the tree is modified, the address should be returned to the root node properly. So for that, at the end of this function, we are going to return the root node. And the reason for this one is in our function, we are not going to declare this root as a global parameter. If you declare it as a global parameter, then there is no need. But I have declared that as a formal parameter, so I'm going to return it. Now let us see the entire function now. So here, insert is the name of the function. We are passing two arguments now. The first one is root, which is a pointer. So we have star here, and it is a pointer to a binary search tree node. So we have the data type as node. Then item to be inserted is given here. And this insert function will return the data to the tree, and it will return the address of the root node. Current root node address will be returned. So the return type should be a pointer because it is returning address of the current root node. So the return type is node star. And don't write void. Void means nothing will be returned. But here we are going to return the address of the root node. So first, all the steps we are going to see one by one now, whatever we have seen so far. First, we are going to check whether root is equal to null. It means the tree is empty. So you insert the new node, right? So first we are allocating the memory. After that, we are storing item in the data field of the new node. Then in the left and the right pointers of the new node, we are storing null value. And finally, we need to update the address of the new node as a router. Otherwise, the pointer will be still null only. So once you do that, you are inserting data to the empty tree. Suppose if your data is less than, if the tree is existing and the data is less than the data of the root node, you are going to insert as a left subtree. So we are passing insert root arrow left comma item. And once that is done, the insert function will return the address. That address, you have to store it in the left pointer of the root node because we are now inserting as a left subtree. Else, you check whether the item is greater than root arrow data. If that is the case, you are going to insert the new item in the right subtree of the root node. So we are going to call the function insert by passing the first parameter as root arrow right. That is the address of the right subtree of the root node. And the next will be passed as item to be inserted. And finally, it will return a pointer. That pointer should be stored as a right subtree of the root node. Instead of null, you will be storing it properly. And this function finally will return the address of the current root node. Now, this is a function for the insert. Now let us see how to perform the delete operation. In case of delete operation, in insert, we have seen that whenever we insert a node, the node will be always inserted as a child left, it will be inserted as a leaf level only. In case of delete, we have seen that in binary search tree, we have three different ways to delete a node. The first one is you can delete a node, that node is a leaf node. Or second one is you are going to delete a node which is going to have only one child. That child can be either a left subtree or a right subtree. And the third case is you are going to delete a node which is having both the children. So we have seen three different cases in the delete. So now let us see how to implement them in the program. So for delete, I am writing a function called a delete node. And to this function, I need to pass two arguments. The first argument is the address of the root node. So I am passing root, and this is a pointer, and it is a pointer to node type. And the second argument is the data you want to delete. And this delete node function will delete the node if it is existing, and then it will return the address of the current root node of the newly formed tree. So you have to return the address to the function which is calling this one. So the return type is now node star. First, let us see all the cases of the delete one by one. First, we are going to check whether the tree is existing or not. And this is a recursive function. So first we are writing the base cases. If root is equal to null, it means that the tree is, that particular tree is not existing. So you have to now return null to the function from where it has been called. So I am returning root. Instead of returning root, you can even write return null also. Okay, so this is a base case. Every recursive function will have a base case which is going to tell you when you are going to terminate your search. Okay, so we are writing this one. This is the base case for the recursive function. Otherwise, now we are going to do all the cases. And remember, when you are deleting your node from the binary search tree, first we have to find out whether the node you are going to delete is existing in the right subtree or existing in the left subtree, or it is the root node of the particular subtree. So you have to find out where the node is currently available. After you find out, then you check whether it is having no children or one child or two children. So those cases you will be checking as second only. So first you find out where the root node is, the node you are going to delete is present. So for that, first I am going to check whether the key is less than root arrow data. It means that the node I am going to delete is present in the left subtree. So no need to go and search in the right subtree. So I'm now going to reduce my search space half of the original search space. That is the advantage of going for binary search tree. Okay, so now since my key is less than root arrow data, I am going to call the function delete recursively, and now I am going to search only in the left subtree of that root node. So I am calling the function delete node again. This time you can see here, first we have passed root as the argument, first argument. Now, since we are going to search only in the left subtree of the root node, we are going to call the function delete node by passing root arrow left as the first argument. We are reducing the search space now to the left subtree. Then pass the key that has to be deleted. And this function will be recursively calling, and whenever it is deleting a node, the address of the newly formed tree will be returned. That you have to again store it as the left pointer of the root node. So that we are doing. Otherwise, you check whether the key you are going to delete is greater than the data available at the root node. If so, don't search in the left subtree, search only in the right subtree. So for that, I'm going to call the function delete node by passing root arrow right as the first argument and key as a second argument. Again, this delete node function will be recursively calling itself till it finds the node to be deleted. Okay, so every time the new search tree will be returned. So for that, we are going to store the address of the root node in root arrow right pointer. Then come to the else part. When it comes to line number 73, it means that you are going to delete a data which is available at the root node itself. Because we have already checked two cases, whether it is less than the root node or right than the root node. Greater than the root node. Now, when it is coming to line number 73, it means that the data we are going to delete is equal to the value of the root node. That means you have found the node to be deleted. Now you go and check the three cases we have seen. So first I am going to check whether the node to be deleted is a leaf node. For that I am writing, if it is a leaf node, the node will be having both the pointers as null. So you have to check by means of pointers only. So if the node to be deleted is a leaf node, the left pointer of the root node as well as the right pointer of the root node will be null. So use AND operator to check this, because both conditions must be true. Then only it is a leaf node. If so, you are going to delete a node which is not having any children. So we have seen that in this case, simply delete the node and return it to the free storage area. So I am going to call the function free. And for free, we need to pass the address of the node to be deleted that is available in the pointer variable root. So you can give that as the argument to the free function. And so once you free that node, now you update root with null, because sometimes there may not be any tree after your process is over. So you have to update the root with null. Then once you update the root with null, you return that new address to the function again. So every time when we are calling the function, we have to return the address of the newly formed tree. So we are returning the root now. So this is the first case. The node to be deleted is a leaf node. And the second case is the node to be deleted is having only one child. So now you have to check whether it is having a right child or the left child. So you need to write two conditions now. The first is in else if I am writing root arrow left is equal to null. It means that the node to be deleted is not having any left child. It is having only right child. So if it is having only right child, so what we are going to do is we are going to update root arrow right in a temporary pointer because the node you are going to delete is having only the right child. So you store the address of the right child in a temporary pointer variable. So I am storing temp is equal to root arrow right. After that, I'm going to free the root node. Okay, that means I'm deleting the root node now. Then what I have to do, I am deleting a node which is having a right child. So now this right child address must be returned to the parent of the node you are deleting. Okay, for that only we are returning temp. We have already seen that when you delete a node which is having only one child, the child will become the child of the parent of the node you are deleting. So for that only, we are storing the address of the child we are deleting in a temporary variable and we are deleting the node. After that, we are returning the address of the child to the parent of the node we are deleting. So the return statement is must. If you don't write it, the address of the child will not be returned to the parent of the node you are deleting. So in line number 86, return temp is doing the work. So now we have deleted a node which is having only the right child. Next, we are going to check whether the node we are going to delete is having only the left child. So if it is having only the left child, the right pointer will be null. So check it else if root arrow right is equal to null. If so, the node we are going to delete is having only the left child. So do the same step again. You store the address of the left child in a temporary variable. After that, delete the root node. Then return the address of the node you are deleting. Not the address of the node you are deleting. Return the address of the child of the node you are deleting to its parent so that this will become the child of its parent. So we are returning temp because temp is having the address of the child of the node we are deleting. So with this, we have seen now three cases. Now let us focus on the final case. The final case is we are going to delete a node and that node is having two children. And we have seen that in this, we can go for two different approaches. When you delete a node which is having two children, you have to find a candidate node. And the candidate node can be either in-order successor or in-order predecessor. We have seen what is the meaning of in-order successor and in-order predecessor. Whenever you have a binary search tree, if you do in-order traversal on the binary search tree, we will always get ascending order. That means you are going to delete a node. Once you delete a node, the binary search tree property should be still satisfied. So what we are going to see is we are going to now pick a node which is having either an immediate greater value when compared to this node or which is having immediate lesser value when compared to this node when you write it in the ascending order. So you go to the ascending order and pick either the predecessor or the successor and replace that instead of this node. So that is called as in-order predecessor or in-order successor. Since we get these from the in-order traversal, we are calling them as in-order predecessor and in-order successor. So now I am going to follow an approach where I am going to replace the node with in-order successor. So if you want to search for the in-order successor, that will be available in the right subtree of the node. Okay, if you search for in-order predecessor, that will be available in the left subtree. So in the right subtree, where my in-order successor will be available. So whatever node you have in the right subtree of a particular node, all the nodes will be greater than this node. And in-order successor will be minimum value node which is present in the right subtree. So now you have to select the candidate which is nothing but minimum value node that is present in the right subtree. So for this, I'm going to call a function min value node. This function will do the job and it will return the address of the node which is having minimum value in the right subtree. So that address I am storing in a temporary pointer variable temp. So declare this temp as node star. Now I'm going to call min value node function. For this function, I need to pass only the address of the right subtree because I am going to search only in the right subtree. So I'm calling this function by root arrow right as the argument. And this function is going to return me a pointer, which is nothing but address of the node which is having the minimum value, I'm storing it in temp. Then what I have to do, once I find the candidate node, either from the right subtree or from the left subtree, I have to copy the value of the candidate node in the root node. So for that, I am writing line number 101, where I am going to store root arrow data as temp arrow data. That means you find the minimum node in the right subtree, copy that minimum value in the root node. So this step 101 is doing that. After that, you have copied the minimum value in the root node. It is in the proper place now. Now you have to delete the minimum value node. You're not going to delete the root node now because you have updated that. You now delete the minimum value node. For that, I'm going to call the function delete node. To this function now, you pass two arguments. The first argument is the address of the root of the tree from where you're going to start your delete process. Now that is nothing but root arrow right, because our element to be deleted is present only in the right subtree of the root node. Then what data you are going to delete? So here I am going to delete a data which is available in the temporary field, because I found the node to be deleted. I have stored in the pointer variable temp. So my data to be deleted is available in the data field of temp. So you can now give the second argument as temp arrow data. So we have seen that delete node function will delete the node and it will return the address of the newly formed tree. So that you store it as a right child of the root node. So once this is done, we will get the node and we will delete it and it will be properly returned. So this is how you can delete a data of a node which is having both the children. Now let us see the min value node function. So min value node is going to accept one argument. That is nothing but address of the root node of a particular subtree. So here it is a right subtree. So I am passing the root address here. After that, you have to select the minimum value node. So how to select the minimum value node? For that, first I am going to store the address of the root node in a temporary variable, because I am going to travel through the entire subtree. I have to find out which node is having the minimum value. So this argument will be changed every time. So I am copying it in a temporary node. After that, you have to go down in the tree to find the leftmost leaf node. That is the node which is having the lowest value. So you search for that node. For that, I am going to check whether temp is not is equal to null. It means I have to travel down. Then temp arrow left is not is equal to null. When you travel down, you have to find the leftmost leaf node. So if the leftmost leaf node is null, no need to travel down. So we are writing two conditions now. While temp is not is equal to null and temp arrow left is not is equal to null. It means that you have to go further to find the node with lowest value. So update the temp now. Temp is now updated as temp arrow left, because I need to search only in the left subtree of temp. So I'm updating it. When I come out of the while loop, it means that I got a node which is having the lowest value, that is the node in the tree as a leftmost leaf. So I have to return the address of that node to the delete node function. So I'm returning temp, because temp is going to contain the address of the minimum value node. So return it. So the data type is node star in the return field of the function. So this is how you can find the minimum value in a right subtree. Now our work is over. So now we are going to see the main function. In the main function, we are going to perform all the primitive operations of the binary search tree. So we are calling cases now. We have to display the menu now. Menu is going to have insert, delete, and traversal. Actually, you can perform any traversal to show the output. Here I am going to do only the in-order traversal. If you want, you can go for even pre-order or post-order. But why I have chosen in-order traversal is, if you do that, you can see that all will be in the ascending order. It will be easy for us to check whether it is a binary search tree or not. So go for always in-order traversal if you want to find out it. So first, from the user, I am going to get the choice. And based upon the choice, I am going to perform insert, delete, or in-order traversal. So if case is equal to 1, I want to insert an element to the tree. So first, from the user, you get the value of the element to be inserted and store it in a field called item. After that, you call the function insert by passing two arguments. The first argument is the address of the root node, and the second argument is item to be inserted. And every time, whenever you call the insert function, it will insert the node in the proper position according to the rules of the binary search tree. And then it will return you the address of the node. So that you have to store it in the root because your tree is updated every time. So store it as the root because root is the address of the root node. Then break it. Then in case 2, we are going to write for element to be deleted. So get the value of the element from the user. After that, call the function delete node, passing two arguments. The first is the root node address and the second is item to be deleted. And delete node also will delete the node and it will return the address of the newly formed tree. So update that in the root pointer. Then go for the case 3. In case 3, we are going to do only in-order traversal. So you check whether root is equal to null. If so, your tree is empty. You can print it. No need to continue your process. Else, you are going to call the function in-order root. So this function I have not explained now because we have already seen in tree traversal how to write a recursive function for in-order, pre-order, post-order, all the things we have seen. So you can make use of that function. You can write it here. So if you see the in-order function, that function is going to have only one argument. You are going to pass only the address of the root of the tree. So that can be passed now. Then in case 4, you can exit from the loop. Otherwise, if the default is there, you can ask the user to enter a valid choice. Then you repeat these steps while choice is not is equal to 4. When choice is 4, you can exit and you can display the result to the user.